Title, Quantum Gates, the moves of the game. Ever played chess? Now picture a game unlike anything you've seen. The board, infinite. The pieces, they pull off moves that seem to bend reality. And the stakes? Oh, just the future of computation itself. Our trusty classical computers, as powerful as they are like players with only pawns, making tiny, predictable steps. But what if you had queens zipping in multiple directions at once, knights that could teleport, and bishops that controlled each other across the whole board in an instant? Sounds like sci-fi, right? Well, it's the dawn of quantum computation, and figuring out its chess moves, its quantum gates, is our ticket to a whole new world of problem solving. Introducing the classical pawns. So before we bring out the quantum superstars, let's give a nod to the trusty pawn. In classical computing, yeah, the stuff in your phone and laptop, information is stored in bits. A bit is like that pawn stuck on one square. It's either a 0 or a 1. Clear cut, no confusion. Think of a light switch. It's either on or off. No dimmer, no maybe. These classical computers do their thing using a handful of rules called logic gates. You've probably heard of and, or, and not. These are the pawn's allowed moves. An AND gate is pretty much saying, if pawn A is on a white square and pawn B is on a white square, then pawn C moves to a white square. A NOT gate? That just flips a bit's state, like a pawn hopping from a black square to a white one. Simple, predictable moves. If you know where things start, you know exactly how they'll end up. And honestly, for a ton of stuff, this pawn army is fantastic. It built the digital world we live in, from sending emails to predicting tomorrow's weather. But some problems? They're like trying to win a chess game that stretches across an entire galaxy using only these pawns. The sheer number of moves, the mind-boggling complexity, it's just too much. For these massive challenges, think designing brand new medicines, creating codes that can't be cracked, or simulating how molecules do their complex dance. Our classical pawns, with their one-step-at-a-time approach, eventually just get stuck. They can only check out one path, one sequence of moves at a time. To win these kinds of epic games, we need pieces with way more impressive tricks up their sleeves. Unveiling the quantum power pieces, the qubit. All right, let's step into the quantum world and meet our star player, the qubit. Now, a classical bit, remember, is like that pawn stuck on one square, 0 or 1. But a qubit? It's more like a ghostly piece that can be on multiple squares at the very same time. Crazy, right? This is a core quantum idea called superposition. Picture a chess piece that isn't just on c4, but is also on d5 and e6, all at once, each with a certain chance of being the spot if you suddenly decide to look. It's not like it's a bit of it here and a bit of it there. It genuinely holds all those possibilities until you measure it. Here's another way to think about it. A classical bit is a coin, flat on the table. It's either heads, that's your 0, or tails, your 1. A qubit, though, is like a spinning coin. While it's spinning, it's not really heads or tails, is it? It's got the potential to be either. Only when it stops spinning, when we actually measure the qubit, does it pick a side and land on heads or tails, becoming a plain old 0 or 1. This superpower of holding multiple states at once means a quantum computer with just a handful of qubits can juggle way more information than a classical computer with the same number of bits. 2 qubits? They can check out 4 states simultaneously. 3 qubits? 8 states. And it just keeps growing, exponentially. It's like your chess pieces are scouting out tons of different game strategies all at the same time. This fundamental difference, this knack for being in many states at once, is what turns qubits from simple pawns into pieces with some serious strategic power. They're the building blocks for all the powerful moves we're about to see in quantum computing. The quantum arsenal introducing key gates. So if qubits are our fancy new chess pieces, then quantum gates are their unique, game-changing moves. And these aren't your pawn's baby steps forward. We're talking maneuvers that play with the very essence of quantum information, letting us do calculations that classical computers can only dream about. There are a bunch of these quantum gates, each with its own special trick, but let's check out a few of the big power moves. First up, the Hadamard gate, or H-gate for short. This one's a real VIP in the quantum playbook because it's how we create that cool superposition thing. Imagine a pawn sitting pretty on square 0. Hit it with a Hadamard gate and boom. That pawn is suddenly in a perfect state of indecision, existing as both 0 and 1 at the same time, with equal chances for each. In our chess game, if a piece is definitely at position X, the Hadamard move is like splitting it, so now it's simultaneously thinking about position X and position Y. This is the move that kicks a qubit into that spinning coin state we mentioned. It's often the very first thing you do in a quantum algorithm, getting everything ready for the computer to explore tons of possibilities at once. Next, meet the Sakura Poly-X gate. This is basically the quantum version of the classical NOT gate. If our qubit was a pawn on square 0, the Poly-X gate flips it to 1, and if it was 1, it flips to 0. Simple flip. If the qubit is already in a superposition, the Poly-X flips the chances of it being 0 or 1. Think of it as a basic color change or position swap. Sounds straightforward, like one chess piece just moving to another square, but don't underestimate it. On the quantum chessboard, even a simple flip can cause all sorts of interesting ripples when combined with other quantum weirdness. Now, this is where it gets really cool. 2-qubit gates, like the controlled NOT gate or KNOT gate. This is where quantum chess starts to feel like a team sport. A C-NOT gate needs 2 qubits, a control qubit and a target qubit. Here's how it plays out. If the control qubit is a 1, then the target qubit gets flipped, like a NOT gate hits it. If the control qubit is a 0, then the target qubit just chills. Nothing happens to it. Imagine 2 of our chess pieces may be miles apart on that infinite board. The C-NOT gate is like a rule saying, if my king, the control piece, is on a white square, then your rook, the target piece, instantly changes its color no matter where it is on the board. This instant connection, this shared destiny, is what we call entanglement. When qubits get entangled, their fates are linked in a way that just doesn't happen in the classical world. If you measure one entangled qubit, you instantly know something about the other, even if it's light years away. The C-NOT gate is one of the main ways we create these super powerful entangled states, which are absolutely key for many quantum algorithms. It's like having 2 chess pieces whose moves are deeply, mysteriously connected, opening up strategies a classical player couldn't even imagine. Of course, there are other important gates, like the Poly-Y and Poly-Z gates, which do different kinds of spins or tweaks to a qubit state, or the swap gate, which, yep, you guessed it, swaps the states of 2 qubits. Each gate is a specific reversible action, adding to the rich set of moves a quantum computer can make. The real magic, though, isn't just in the individual gates, but in how you string them together. The quantum strategy, circuits and algorithms. Okay, so you've got these powerful chess pieces and you know they're cool moves. But how do you actually win the game? You need a strategy, right? In quantum computing, that strategy takes the shape of quantum circuits and quantum algorithms. A quantum circuit is basically a planned sequence of quantum gates that you apply to your qubits. Think of it like a chess player planning a series of moves to outsmart their opponent or corner their king. Typically, you start by setting up your qubits, often just to a simple state like all zeros. Then, you unleash a carefully designed sequence of gates, Hadamards to get that superposition going, C-NOTs to create entanglement, and other gates to tweak the states just so. These gates lead the qubits on a wild dance through an enormous computational space, checking out tons of possibilities at once, all thanks to superposition and entanglement. And at the very end, you measure the qubits. This measurement makes their quantum states collapse into regular classical bits, zeros and ones. And that's your answer. Imagine a quantum chess grandmaster with these superpowered pieces. They're not just moving one piece, then another. Nope. They use Hadamards to get pieces exploring multiple paths all at once. They use C-NOTs for coordinated attacks, where one piece's state instantly affects another, even across the board. They line up these moves, that's the quantum algorithm, in such a clever way that the bad paths, the wrong answers, kind of cancel each other out. That's another bit of quantum magic called interference. Meanwhile, the paths leading to the right answer reinforce each other, making them the most likely outcome. And that's the secret sauce. That's how quantum computers can take on problems that totally stump classical computers. Take Shor's algorithm, for instance. It's a famous quantum algorithm that can factor huge numbers way faster than any classical algorithm we know, which, by the way, could shake up a lot of modern encryption. Then there's Grover's algorithm, which gives a nice speed boost for searching through unsorted data. These algorithms are like specific game plans, strategic sequences of quantum gate moves, built to use the strange and awesome rules of the quantum chessboard to find answers that classical pawns might take billions of years to just trip over. The bigger picture, winning the game. So what's winning the game actually look like when we're talking quantum computing? It means cracking some of the world's toughest, most urgent problems. Being able to simulate molecules with mind-blowing accuracy could totally change the game for drug discovery and creating new materials. Think new medicines, super efficient batteries, or amazing new catalysts. Can you imagine designing a drug by knowing exactly how it'll react with proteins in your body? Or whipping up a new material for solar panels by simulating its quantum behavior? That's the kind of thing we're talking about. And then there are optimization problems. Those pop up everywhere, from logistics and finance to AI. Finding the absolute best route for a global shipping network, or fine-tuning financial models with a gazillion variables? These are the kinds of puzzles where quantum computers are expected to really shine. Even super complex machine learning models could potentially be trained much faster. Look, this isn't just about building speedier computers in the old-fashioned sense. It's about unlocking completely new ways of computing, taking on problems that are currently just unsolvable. Not because we don't have enough processing grunt, but because classical computers are essentially playing with a limited toolkit, the wrong kind of pieces for these specific games. Quantum gates, with their power to create superposition and entanglement, offer a completely different, and for certain problems, way more powerful, method to handle information. They're the ticket to understanding these complex systems and winning these incredibly difficult computational challenges, the catch and the checkmate. Now let's be real. Building and running these quantum chessboards is a massive headache. Qubits are incredibly fragile. The tiniest little disturbance from their surroundings, a stray vibration, a tiny bit of heat, can make them lose their quantum magic. This is called decoherence. It's like someone accidentally bumps our ghostly superpositioned chess pieces, making them suddenly pick a square and poof. There goes their quantum edge. Keeping that quantum state stable long enough to do tricky calculations? That's a huge engineering challenge. And here's another thing. Quantum computers aren't a magic bullet for everything. For lots of everyday computer tasks, our classical pawns are still the champs. They're perfectly fine and often more efficient. Quantum computers are more like specialized power tools, designed for those really specific, super tough problems where their unique moves give them a serious advantage. Figuring out exactly which problems are quantum winnable is something scientists are actively working on. But even with all these hurdles, that dream of delivering checkmate to problems we once thought were impossible, that's what's fueling the worldwide push to build bigger, better, and more stable quantum computers. The moves of the game, the Hadamard, the C0, and all their buddies, aren't just ideas on a whiteboard. They're the actual tools scientists and engineers are using to build machines that could completely rewrite the rules of what's possible. The quantum chessboard is being set up, the pieces are being made, and the strategies are taking shape for a whole new age of computation. This whole journey into the quantum chessboard is really just getting started. What part of this quantum strategy blows your mind the most? Got a killer analogy for another quantum gate? Drop it in the comments below. We'd love to hear it. And if you're keen to keep exploring the wonderfully weird world of quantum mechanics and its epic computational showdowns, definitely hit that like button and subscribe for more adventures. So, we've gone from classical pawns making their predictable marches to quantum queens dancing through superpositions and tangling up across huge distances. It's pretty clear the moves of the game in computing are going through a massive shift. These quantum gates we've chatted about? They're not just abstract operations. They're the basic actions that let us speak the language of the quantum realm, a language that could unlock solutions to problems we once thought were totally out of reach. That infinite quantum chessboard is spread out, and we're all just starting to figure out its most powerful opening moves. The game is definitely on.